So welcome back. So what we have now, so just talking a little bit more about this because I kind of rushed through it at the end. And this is basically a shell of charge, so the positives or the negatives are all on this shell. And in one case I'm outside, and again we get the same old, same old. It doesn't matter if you have a point source of charge or you have a ball of charge or you have a sphere of charge, a shell of charge. If you're outside and it's an inverse square law. And you can't be inside a point source of charge, but if you're inside a ball of charge or you're inside of a shell of charge, then you get different outcomes. If you're inside the ball of charge, what happens is that you get a steadily increasing electric field until you get to the surface of the ball, and then you get the inverse square. And if you're inside of shell of charge, you get a zero electric field until you're at the surface, and then you get an inverse square. This fact that you do not have an electric field inside a shell of charge is incredibly useful. No electric field means no force on a charge. And U consists of charges, you know. So no electric field on U is nice. A big electric field and all your electrons will want to go one way and all your protons will get left behind or go the other way, and you'll start to polarize. And that's not good. I mean, that's not good. So we don't like big electric fields. Big electric fields tend to cause things to arc across anyway. So, especially if I'm with high voltages, then I'd like to have a safe environment where I can work with high voltages. So, for instance, back in the day when they wanted to do a lot of work with, well, even now, but back in the day when they did a lot of the atomic work where they wanted to do alpha particle scattering or they wanted to fire protons into atoms' nuclei. Or even now with electron beams, you want to send an electron beam into a material and you want very high resolution, so you want very small electrons, so you do basically high voltage. You got this machine and it could have millions of electron volts of potential, millions of volts of electric potential, and you got to operate it, you got to work with it, you got to touch something that's connected to it. And you don't want your employees to get zapped, you know, every now and then. So you want to try and make them as safe as possible. And one of the ways you can make them as safe as possible is a Faraday cage, where you basically put them in a wire mesh. And the idea is that if a strike comes along and hits the outside of the mesh, so you put a whole bunch of charge onto this shell, there's still no electric field inside. So it can strike the outside and it will not cause any electrical forces inside because there's no electric field. So it's very, very nice. And in fact, you know, when I was doing my graduate work, I was working on a thing called a Cockcroft-Walton accelerator to implant ions into materials. And they had the same problem. What they'd do is they'd have these people inside, the operators would be inside a cage, and they'd have like a little perspex window, and in that window would be the end of a wooden dowel, which would go like 3 feet or 2 feet to the control panel, which had the voltage controls and everything on it. So they would turn a piece of wood which turned a knob on the end of a piece of electrical equipment that was connected to very high voltages. And they were safe. The wood would not conduct, so they'd be safe from that, and they were inside a Faraday cage, and they'd be safe from that. So really it's quite valuable. By the same token, sometimes you have problems with it. So for example, my brother had some drywall done on his house, and the drywall came with an aluminum backing. And the aluminum backing is conductive. And Britain being Britain, it's very kind of humid and damp. And he noticed that his wireless reception in that room was awful. And he could go like outside and it was fine, but inside that room it was awful. And what he reckoned in the end was happening was that the aluminum sheets were forming basics, you know, a fair amount of a Faraday cage. And then you're trying to get, you know, an EM field where you're trying to get electric field in there, and you've been shielded from that. So sometimes it fights against you, and sometimes it goes for you. It's kind of useful. Yeah.
If the shell were negatively charged, would it matter, or would it change whether or not there was charge inside?
No, it's negative. Then all you have is, for the electric field, would have a different sign.
Okay.
Yeah. So if it's negative, put down a negative sign. If it's positive, put down a positive sign. And that makes sense, doesn't it? It's like, you know. Let's do one that's a bit more interesting. And for this one, we can't use a spherically symmetrical Gaussian surface because we don't have a spherically symmetrical body. We have a wire of charge. And it's infinitely long, just so that we don't have to worry about calculating the end effects. Infinitely long. And we've got to work out the charge at a certain point, and the electric field at a certain point. Well, I did the point over here. A certain point. And we get this wacky electric field is equal to 2, which is a constant. Ke is a constant. R is how far I am away from the wire. And then this lambda. And this lambda is the charge per length. It's the linear charge density on that wire. That's how that goes. So let's do it. So the first thing we're going to do is draw ourselves a nice infinitely long piece of wire. And we're going to take our point of interest, P. And again, I'm going to come down here. Actually, let's for the sake of it, I've been doing pretty good so far. So let's just keep that the same color. So there's my charged rod. And then I'm going to get myself a good old Gaussian surface. So now, I can't do a spherical surface. It's got to go through this point P. So what would it be? And frankly, if I'd never seen this problem before, I'd be scratching my head and kind of going, well, we've got these things, and there's a cylindrical symmetry. So let's try that. I'm not sure I would be as smart as this, but I like to think I was as smart as this. So let's try something like this. I think I'd just sit there for a while and kind of sigh. But let's try this. I've got a cylinder. I have 3 bits to the cylinder. There's the top, which I'm going to call part I. There's the bottom, which I'm going to call II. And there's the sleeve, and I'm going to call it III. I don't want to use letters because A is already used up with area. That's just going to confuse the heck out of me. So I'm going to use Roman numerals. In this point of interest, my electric field, because it's infinitely long, my electric field is going to be radially away from the line. That makes sense, doesn't it? And because I used a Gaussian surface, my dA is also, in that bit, is radial, yeah? Here, not so lucky. There's my E, and there's my dA. And here is my E, and there's my dA. So I have 3 different bits. So let's say 4, 1. Oh, sorry, no. The flux equals the integral of vector E dotted with dA, which equals Q inside over epsilon naught. For 1 and 2, E is perpendicular to dA. So E dot dA, which equals E times dA times the cosine of 90. And that, of course, is equal to 0. Cosine of 90 equals 0, yeah? So the flux, so they go away, yeah? Because E dot dA equals 0. Yeah? So they've got no E left in them, so forget it. For 3, E is parallel to dA. So we get that our flux is equal to E, integral of E, times dA, which equals the Q inside over epsilon. E is constant on, is it 3 I'm trying to draw? Yeah, 3. That should be 3. E is constant on 3. So flux is equal to E times the integral of dA, which equals Qn over epsilon naught. Oh, well, now again comes your geometrical shapes. The integral of dA in this case is equal to, what would it be? What's the area of that sleeve? Yep. Yep.
2 pi r h.
Excellent. 2 pi r times h. So that flux is equal to E times 2 pi r circumference times h, which equals Q inside over epsilon naught. Let's just clear this up a little bit. So E is equal to Qn over 2 pi r h times epsilon naught. And Ke is equal to 1 over 4 pi epsilon naught. So epsilon naught is equal to 1 over 4 pi Ke. So E is equal to Qn over 2 pi r h. And then instead of epsilon naught, I'm going to put down 1 over 4 pi Ke, which gives me 4 pi Ke goes to top. Qn over 2 pi r h, which equals, well, the pi's cancelled, so I get 2 Ke Qn over RH. Now, what is my Q inside? Qn is equal to, it's going to be H times lambda, where lambda is linear charge density, which is that guy. So E is equal to 2ke h lambda over RH, which equals 2ke lambda over R. Which in this case is equal to 2ke times 6 over 2, which equals 6ke newtons per coulomb meter squared. My pen's not behaving very well today. It's a little bit of a lag in my writing. I can't plot E inside the wire. But if I plot E versus R, what I see, it's not an inverse square relationship. It's an inverse relationship. Yeah, it's a 1 over R relationship. Yeah. And that, you could kind of guess that with a sphere. The area goes as 4 pi r squared. With a cylinder, the symmetry goes as 2 pi r. You know, you can kind of see it from the symmetry, but cool. That is a good question. And that's a good question. If I give you one of these others where it's outside, it's a bit of a gift because the charge inside is the charge inside, you know. I'm not above it, but the two that, you know, if you want to know how hard does it get, do where the charge is inside or do the linear line. If you can do those two, you should be able to do the other two. And again, I want to see the steps. I'll give you a lot of page for it. I'll give you a page for this and you know, take your time. I'm not going to ask you this one. It's just I run out of time. But basically, let's just talk about it a little bit. This is a wall of charge. Again, I'm looking for symmetries, and it's not obvious, but if you pick a cylinder which goes through the wall of charge, then on the sleeve, the electric field is outwards, and my area vector is that way, so there's no contribution from the sleeve, because they're at 90 degrees. So the only places where there's contribution are these ends. And rather than talking about a linear charge density, I talk about an area charge density. You know. So as an exercise, if you want to, I won't ask you it as a question, but if you want to say, have I got this down? Have a go at that. And the trick is, knowing the Gaussian surface comes in 2 parts, and you're symmetrical. You're as far in front as you are behind, because that matters. But for fun, have a go at it. If you can do that, then you got the whole thing mastered. And if you get stuck, just look back in the note. I think maybe not in the notes, but certainly in the book, but maybe on those online videos that I did, it might be there. Last little thing is, okay, so we have not a ball of charge, but we have an electric conductor. So it's like a shell of charge. Electric conductor is like a shell of charge because all of the charges want to stay as far away as they can from each other. So they all tend to sit on the outside skin. And your electric field lines come at 90 degrees. This is positive charge or negative charge. Can you tell by the field line direction? These are E lines. Is it positive charge or negative charge? It's positive, isn't it? Because the boulders are rolling away. So that's positive charge, but it's all on the skin. And what you find is that the charges want to get away from each other, but they tend to congregate around points. Needles are really interesting. The electric field lines get crunched up together at needles, and so you tend to have high electric fields there. We use this to our advantage. In a flat panel TV, if you were to look behind, you'd see a whole array of silicon needle points. In fact, so to tell you, one of the coincidences of my life is that my PhD supervisor did work on electron field emitters. And it was basically, he sharpened metals needles to a point, and he'd look at how easy it was to get the electrons to be emitted. It's hard to get electrons out of a metal. There's a thing called the work function. You've got to overcome it. If you can somehow reduce the work function, then you can get electrons out a lot easier. So one of the ways is you use a field emitter. It works in vacuum. It's like. And then when I came to the States, not my first boss, but my second boss, the guy who got me the green card, the guy who hired me, so I got a green card, the guy who became something of a mentor for me in terms of, in fact, they're both mentors in their own way. He also worked on field emitters. It's like the most amazing thing. I had nothing in any of my research to do with field emitters. They don't have a thing to do with it. It's just what they did for their research. So when they met, they were like quite chatty. Oh, you did. Oh, And then there were, so then I'm paying interest because I'm having lunch with them, and it's kind of like, so what are these things useful for? And I said, well, it's kind of a bit abstract, and And then a few years later, the guy, my guy is the University of Florida, just is long gone from there, but he was talking about how you could get a silicon wafer and you could make an array of field emitters. And using semiconductor techniques, you could individually electrify the individual needles. And you could have these electrons spray out onto a screen and cause light or no light. And you could use this for displays. And my thought was, this was back in 1980, probably 85, 86. My thought was, well, that's never going to happen. Because, you'd have to line them up perfectly and, And then years later, my boss at USF bought a plasma TV. And that's exactly how it works. It's like, and consistently, I underestimate what engineering can do. I say, well, in principle it could work, but it's never going to work in practice. And engineers get it to work. And they get it to work for less and less money. And it works very nice. But this idea is the idea behind the photocopier, relies on this. Plasma TVs or, flat panel TVs rely on this. And actually, the lightning rod relies on this, because the lightning rod, as we'll find out next time, the lightning rod is not about having a nice big conductor to the ground. It's not so that if you get struck, there's a nice current path to ground. That's true. But the idea is you don't want your building to be struck in the first place. And so if you put a pointed needle on the top of your building, when that cloud, which is charged, floats above and induces the negative charges in your building, they spray out. And so this positive charge cloud does not see your building. It sees the tree next to it and strikes that, because the tree could not discharge itself so easily, whereas this point on the top of your building will discharge itself so easily. It's a really, really good idea. The idea is you discharge the building so that it does not attract the lightning bolt. This was invented by, anybody know who invented this? Benjamin Franklin. It was one of his inventions. And Benjamin Franklin was just post the rebellion. I'm American, so it's like I can see things from both sides. But in fact, in English history, we didn't learn anything about America. I did about that period, and it was not mentioned. It was like just never happened. And after the War of Independence, the last thing that British establishment wanted was American scientists proving their worth. So when Benjamin Franklin published this, the argument was, well, we've already done that. Oh, really? Oh, yeah, look, here's the sketches. And they had lightning rods that were like that. Which, if you think about it, based on this diagram, is the last thing you want. Because this is not going to discharge. This is actually going to dangle, temptingly, a whole bunch of negative charges below the cloud. So British lightning rods probably were used to conduct the current to ground before it set your building on fire, whereas American ones discharged. So it's kind of interesting historical bit about the rivalries. We're done, so I'll continue. I thought I'd get to voltage today, and I didn't, so...